Hello, pre-calculus students. In this video, we're going to cover some new identities in trigonometry, some double angle identities, half angle identities, and a couple of other ones. I'm going to keep the explanations short in this video so that this will mostly just be kind of brief explanations. We'll go over it in much more detail in class. So, if we take two angles, U and V, and we add the two angles together and take their sine, we'll get this formula. That's the sum formula for sine. We've already derived that. Now, if you want to double an angle, U and V are the same angle, it's just U plus U, and that will simplify to this formula. Similarly, tangent would simplify to this formula, but the fun one is cosine. If you just substitute into the original formula, you get this one, but we know that cosine squared u is 1 minus sine squared u, so if you make that substitution, you get this formula for cosine of 2u. And we know that sine squared of u is 1 minus cosine squared of u. So if you make that substitution, you get this third formula for cosine of 2u. So those are our double angle identities for sine, tangent, and 3 of them for cosine. And here are the half angle identities. Note if we have cosine of 2u, that's 1 minus sine squared of u. We just derived that through some algebra. We can get down to this equation. So then we just make a substitution. Let's let alpha be 2u. So u is alpha over 2, and this just becomes 2u is just alpha. So if you want to take an angle, take half of it, and then take the sine, here's the formula you use. And similarly, for the other half angle formulas on page 385 of our current textbook. There are some power reducing formulas. So if you have sine squared of u, you can get rid of the squared from this identity, and now it's cosine to the first power, but it's 2u. So these are the three power reducing formulas. Here's an example. So we have cosine of 2x plus cosine of x equals 0. What's x? Well, we can replace cosine of 2x with that double angle identity. Now we have what looks like a polynomial. We could certainly write it as a polynomial if we did m equals cosine x. But we don't have to do that. We could just do the substitutions anyway. -1 times 2 is -2. The 1 cosine x here. These two numbers exist. They multiply to give -2 and add to give 1. Since they exist, this is factorable. So I rewrite the cosine x as 2 cosine x minus x, the 2 and the -1. Do my factoring. Get cosine x equals 1/2, which means x is either 60 degrees plus 360k and 300 degrees plus 360k, or it's equivalent in radians. Do not mix degrees and radians. Don't say 60 degrees plus 2 pi k. We don't mix degrees and radians. Degrees get degrees, radians get radians. Then over here, cosine x is -1. We can write the answer in either degrees or radians. So here are all possible answers in both degrees and radians that will satisfy this equation. Now let's say that I tell you that the sine of theta is 3/5 and that theta is in the first quadrant. What is the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta? So if sine theta is 3/5, we double that. Are we going to get a number in the first quadrant or the second quadrant if we double the angle? It's going to be hard to tell until we do some math. So we could do the Pythagorean identity and get cosine as 4/5, and we know it's positive because theta's in the first quadrant. And tangent is sine theta over cosine theta, which is positive 3/4. I now know sine theta, cosine theta, and tangent theta. So I can do the sine of 2 theta, substitute the numbers in. The cosine of 2 theta, substitute the numbers in, and tangent of 2 theta. One thing I want to point out is that a common mistake is to say 2 sine theta cosine theta. Somebody's going to write 2 times the sine of 3/5. And that is not correct. The sine of theta is 3/5. So it's not the sine of 3/5. So you can see that our angle, twice this angle, is going to be pretty close to 90 because the sine of 2 theta is 24/25, which is very close to 1. But we still don't know if it's in the first or second quadrant. When we get cosine of 2 theta, you see that we get 7/25, which is a small positive number. So our answer is obviously now in the first quadrant. 2 theta is in the first quadrant. And tangent is 24/7. Now here's a fun one. Tangent to the 4th of x. Now it's tangent squared. I do the power reducing formula for tangent. Then I FOIL this out. Now if we let u equal 2x, then cosine squared of u is what? Now we end up with this thing here with a fraction, and numerator and denominator, just going to multiply top and bottom of the fraction by 2 to get rid of these internal fractions. And it simplifies, if you want to call it simple, it'll simplify to this. So tangent to the 4th of x, we want to get rid of that 4th power, would simplify to this. Now, let's say for whatever crazy reason, we want to find the cosine of 22.5 degrees. Well, you happen to know that 22.5 degrees is half of 45. So we can take the cosine of 45 degrees over 2 and we use our half angle identity, because this is half of 45. Notice that we put cosine of 45 degrees in here, because if it's cosine of u over 2, it's 1 plus cosine u in the numerator under the radical sign. So the cosine of 45 degrees is root 2 over 2. To get rid of the fraction, we multiply top and bottom by 2. Now this 4 is under the radical, so the square root of 4 is 2. So this is the cosine of 22.5 degrees. Because 22.5 degrees is in the first quadrant, I know that that cosine is going to be positive. So you can take the cosine of 22.5 degrees with your double box, do this calculation, and you'll get the same values. Now, just for giggles, we know that the cosine of 30 degrees is root 3 over 2, because that's a unit circle value. But let's see what the half angle identity gives us. So 30 degrees is 60 degrees over 2. So under the radical, it's 1 plus the cosine of 60 degrees all over 2. Cosine of 60 degrees is 1/2. Let's get rid of that internal fraction. And we get √3/2, which is the cosine of 30. So that just shows us that we can use the half angle identity, and we're going to get the same answer that we knew we should. There are about 8 zillion different identities with trig functions. We're going to only worry about the ones we've seen today, the double angle and the half angle and a little bit of that power reducing identities. So that's all I have for you for this video. Have a great day.